Hello everyone. So welcome back to the course on architectural design of ICs. So in the last class we have seen that means circuit for running average system. So that means we have seen three different type of architecture. So if we go for the parallel architecture, so that means parallel implementation of the running average system. So at that time it gives me some advantage, it has some disadvantage. So then we have gone for another architecture which is sequential or serial, that means architecture. So it is also, that means area I can save, whereas in terms of in terms of speed. So then we have find out, that means as in parallel implementation we are getting the speed in terms of area, whereas we are getting in sequential implementation of that we are getting that the area in terms of computation time or in terms of speed. Okay. So to get both the benefit of these two particular circuits, so we have developed one combined circuit, and there we can see that okay, we are getting this with minimal that means increment from the sequential element or sequential architecture, we are getting this computation time we are also making lesser, and the area requirement also becomes lesser. Okay. So today we will start with another that means topic which is very much common in architectural design of ICs. This is one techniques. This is not one, basically we will discuss about two techniques which is very much useful in architectural design of ICs. There one is pipelining and another one is parallel processing. Okay. So I think most of you have seen this multi-core architecture. So these are nothing but this parallel processing. Okay. So to increase the corresponding frequency of the circuit. So in the architecture, why I need to learn these two particular like pipelining technique and parallel processing technique. So till now what we have seen, suppose we have some algorithm, right. So from that particular point of algorithm, now we can choose different type of architectural implementation of that. So if we have done that architectural implementation, so after doing all this optimization, okay, so whether that is algorithmic optimization or this architectural optimization, the speed is now that is final. So I cannot go beyond that, whatever optimization, that means the full optimization of the circuit or the logical expression that we have done. Okay. But still the requirement of timing that is not meeting. So at that time what I will do, so that I can increase the corresponding operating frequency of the circuit. So pipeline is one of the technique which basically increases the corresponding operating frequency of the technique. So we will see that what is this pipelining technique, and after doing the pipelining, still if it is not meeting the corresponding sampling frequency or the operating frequency of the circuit, then we can go for the parallel processing too. So what are the meanings of this pipelining, what are the, that means techniques for doing the pipelining, and what is parallel processing, that we will see in this particular lecture. Okay. So pipelining transformation says that it leads to a reduction in the critical path which can be exploited to increase the clock speed or to reduce the power consumption at same speed. That means whenever we use this pipelining technique, at that time we can that means the main fundamental is that once we have done this architectural optimization, that means after doing the algorithmic optimization we have find out the minimal, and after the architectural optimization we have find out the minimal logical expression for that particular logic or that particular output variables, right. So I cannot change more than that. So at that time what I will do, but I need the, or my requirement of the critical time that is lesser than that, whatever I am achieving after this optimization of this architectural as well as the algorithmic optimization. So at that time I have to follow this pipelining technique which can reduce the corresponding critical path by means, that means it is increasing the clock speed or the sampling speed, and apart from that it is also reducing the power too. In the same manner, the parallel processing, basically what it does, it multiples the, that means it copies the number of processing element, and therefore, as the processing is basically done in parallel, so that is why the clock period again I can increase, that is more than this pipelining technique. Okay. So, it says that in the parallel processing, multiple outputs are computed in parallel in a clock period, therefore, the effective sampling speed is increased by the level of parallelism. So, this means actually in our basic mathematics course we have learned these things. Suppose one work I have to do, right. So, if I can employ 5 workers to do that job, it takes, let us consider, 1 day of time. But if I, that means employ 25 of that means 25 number of employees or the workers to do the same job, so at that time is that the day will remain same? No, because I am increasing the processing power. I am employing more of the workers means I am increasing the processing powers. So, okay. So, that means the computation time will be now reduced. So, here how much time I have increased? So, that means initially it was 5, that means 5 workers, now it becomes 25 workers. So, that means 5 level of increment I have done in the processing powers. So, that means the computation time which was 1 day, so that will be reduced now by 1 by 5. So, here also the same principle that is works here, that means whenever we are doing this parallelism, that means suppose the level of parallelism is chosen as n. So, that means I can increase the clock speed or the sample speed by a factor of n. It is not that only the factor, that means this clock speed or sampling speed will increase, the corresponding power will also be decreased by the factor of n 2. So, if I use, that means combining this pipelining technique and parallel processing, suppose pipelining level I have used of m and parallel processing level if I used of n level. So, in that that means corresponding, if I in one particular circuit, whenever we are doing that architecture of that, so at that time both of these techniques if we imply or impose on that particular circuit, so at that time I will get m into n level of improvement in the performance of that particular system. Okay, so, how not only the sampling speed, but as well as the corresponding that means in the power level also I can reduce by that factor of m into n. So, that how we do, and we will take one example of that, and then we will see how we can reduce that thing. Okay. So, here you see this is nothing but one that means one just simple addition operation in a chain. Suppose here what we are doing n a n into x n, and whenever we are doing this pipelining or parallel processing, at that time what is my intention? All the times it should be remembered or it should be in your mind that the functionality will remain same, it will not change. Okay. So, that means what we are doing, a n x n is added, then that is added with b n, and we are finally producing y n. Now, according to this pipelining technique, what is there? That means in between, now this is my critical path, this x n to y n or this a n to y n, any of these two paths is the critical path, maximum of these two, which is taking the maximum time for computation. So, that is the critical path of this particular circuit, right. So, now I have to reduce this critical path to optimize the sampling speed or the clock speed. I have to reduce or I have to break this path. So, how can I break? So, if I put in between these two, if I put one delay over here, or the resistor over here. So, at that time these two combinatorial circuit will be act as different. Why different? Because if as I am putting the resistor, so that means now the corresponding output from this adder, that will be in one clock, particular clock, that will be stored, and then in the next clock it will be added with this. It will not happen in the same clock edge. So, that means now this will act as individual, this adder will act as individual of this. So, that means now initially as there were in this particular circuit, the delay was 2 adder delay, but now for this, as I have put the resistor in between, so the delay of this particular circuit becomes only 1 adder. So, that means I am increasing the operating speed by a factor of 2. Okay. So, that means now initially what I require, I require 2 adder. So, here I require only 1 adder delay. So, that means by 50% I have increased the sampling speed. So, if it was suppose if it is let us say 1 nanosecond, and this is, that means the adder delay is 1 nanosecond. So, initially the total delay was 2 nanosecond, but now for this particular circuit it will become only 1 nanosecond. So, that means if it is 500 megahertz sampling speed, so here it will become 1 gigahertz. So, not actually technically if I say, that is not exactly 1 nanosecond, because the clock to Q, that means the resistor will also have some delay which will be associated with this. So, that delay also I have to consider for this particular case. Okay. So, that means it will not be, why we are considering, because as this in compared to this adder, the delay for this resistor which is very much nominal. So, that is why we can we can ignore the delay of this resistor. This D means this is nothing but a resistor. So, we can that means ignore those delays, and that is why we can say that okay, 1 nanosecond is the delay for this particular circuit. Okay. Now, what we are doing in the parallel processing, these two particular elements now I have copied. Okay. So, this is one processing element, the combination of this, if I say that this is one processing element. So, if I imply or if I impose 2 of them, so that means now the number of samples I can produce 2 at a time. That means here I can for this particular processing element I can put x 2k, and here I can that means put x 2k plus 1. That means, and I can produce the y 2k and y 2k 1 at the same time. Okay. So, that means if I used 2 number of process, that means if I copy the processing element by a factor of 2, again I can increase the sampling speed by a factor of 2. Okay. Means what? Basically, if I just means what? Initially what was happening? This x0, what I have to do? This x0, x1, x2, x3, the samples are coming like this, right. But whenever I have used these 2 particular processing element, this is P1, this is PE2, let us consider this. So, at the time what will happen? X0 I can process over here, and x1 I can process over here. If I am having only one processing element, so at that time what this particular source will be connected to this. So, that means first it will process x0, then I will get y0, then it will start with x1, then I will produce y1, then y2, y3, something like this it will produce. But in this case what will happen? So, x0 will be processed here and x1 will be processed here. So, that means y1 now it will come here, y3 will come here. That means the even samples that will be processed by this, if I put the even number of sample at this particular processing element, and this odd number of processing element if I just want to pass through this P2. So, at that time the even number of output I will get odd number of outputs I will get at this particular output of this processing element block. So, that means now if my that means after this processing element, if 1 gigahertz was the that means sampling speed, now I can increase as I need to produce that 2 of the samples within 1 nanosecond. Otherwise, what will happen? This will remain idle. If I just at 1, if my clock period is now, that means sample clock period is 1 nanosecond. So, this will come at 1 nanosecond, then this will come at 1 nanosecond, but at that time it will just remain idle. One of this particular element that will remain idle. So, the sampling speed I need, that will be 0.5, so that within 1 nanosecond it produce x0 and x1 both. So, it will take this particular example, that means this sample, then it will produce y0 and y1 after 1 nanosecond. Okay. So, whenever we are talking this, that means whenever we are talking about this, so at that time there are some terms which are very much that means associated with this particular pipelining and parallel processing things. One is that latency. What is that latency? Latency is the, that means the time requirement from applying the input to get the output, how much clock period I need to wait. So, that is basically known as the latency of that particular circuit. What I said, that after applying the input, after how much clock cycle I have to wait, that means I am getting the output after how much clock cycle, that number is the latency for that particular circuit. So, if I just consider this particular case, so at this at this particular case, as there is no resistor in between, so initially combinatorial circuit means whenever there is a change in the input, immediately the output basically that reacts or that comes out. Okay. So, as there is no resistor in between these two adder path, so whenever I will apply whatever is the delay for that adder, the output will change here. So, again after that again this will be connected. So, this will affect the corresponding yn. But here as I have put the delay in between, that means I will that means in 1 clock I have just get the output over here, I have to wait for 1 clock, and after that in the next clock I will get the y1. So, once I got the y0, after that again immediately I will get the output in a flow. It is something like a, so why this pipelining, that means terms comes, it is just like if you want to pass the water from a pipe. So, whenever you have connected to the tap, so at the time whatever is the length of the pipe, so it will take some time from the first flow which is applied in the, that means the front of the tap, to for achieving to the outlet of the pipe. So, it will take some time for traversing the water through the pipe. So, if I increase the length of the pipe, the more the time I require to that means to flow the water through the pipe from the top, that means from the tap's point. So, here also the same thing. So, but the thing is that once I got the output at the, that means pipe's front, after that the flow is continuous, I do not have to wait. So, initially I have to wait for that particular time, and that time is basically very much related to the length of the pipe. So, here also the same thing, whatever the level of pipelining I will introduce into the circuit, so I have to wait for that much of clock period here, which is known as the latency for this particular circuit. Okay. And now the thing is that, now suppose Okay, so this is the okay. I am just I will discuss that later. So this is the that means the latency that the definition of latency. Now there is another term which is throughput. Throughput means per unit of time how many output I am getting after applying the corresponding input. Means what? If I have that means for this pipelining things, what I have done, I have applied this input over here, and after that I am getting at the output which is n minus 1. So that means per unit of time what I am getting, I am applying 1 and I am getting 1 output at the end. So that means the throughput is basically 1 over here. Now if I use, that means if I just copies that processing element, as in this case I have copied that by 2. So that means within that unit time I am getting 2 number of samples at the output, which are this y2k and y2k plus 1. Okay. So that is why here the throughput is that the number of output I am getting within the unit time of that means within this unit time after applying the inputs. So that is known as, that number is known as the throughput, and throughput is very much related to the corresponding this parallel processing. So what I said, latency is related to pipelining and throughput is related to parallel processing. Okay. So these two is the two things which I require, and another thing is that is the speed up. Okay. So what is the speed up? Speed up means that means by what factor I am increasing the sampling speed or the clock speed. So in this particular case, what is my speed up for the pipelining things? What is my speed up? So initially what I said, that there is 2 adder delay. So now I have just come to the 1 adder delay. That means the speed up is now 2. So 2 adder delay divided by 1 adder delay. So that means the number of speed up is 2. Then again, as I have employed 2 parallel processing element, so that means again I have increasing the sampling speed. Now there it becomes the corresponding, that means the sampling speed, that means sampling clock period, that instead of 1 nanosecond now it becomes 0.5 nanosecond. So that means now I require the corresponding, that means the increasing the speed up by again 2. So initially in these two particular case, if this is 1 nanosecond and this is 1 nanosecond. Okay. So this, for this A case, the minimum clock period which I require, that is 2 nanosecond, right. But for B case, the minimum clock period requirement, that becomes 1 nanosecond. So that means here I am increasing the speed by 2. In the C case, the same, that means the clock period will become, that will be 0.5 nanosecond. So that means I have started with 2 nanosecond after employing pipelining along with parallel processing. So I have come down to the 0.5. So the speed is now, speed up is now 2 nanosecond divided by 0.5, which is basically 4. So this is the speed up of this particular circuit. Okay. So this is the, that means fundamentals of pipelining and parallel processing. Okay. So then, so if I say that this is, that means here this is a basic idea. So in parallel, in pipelining, what will done? Suppose P1 is A1, B1, C1 and it passes through the corresponding register. So now it will be delayed as it has passed through one that register. So it will become A2, B2, C2, then D2, that means it will be just delayed by 1 clock cycle. Then P3 again it will be delayed by again 1 clock cycle, then again at the P4 it will be again delayed by another clock cycles. But in parallel processing what happens, this A1 that means for A it will be processed, for P2 it will be processed, for P3 again this will be processed, that means all the processing are running in parallel. Okay. So, this is the basic idea, that means difference or this is the basic ideas of parallel processing and pipelining. Okay. So, this is that means the data dependency or the data flow of this particular circuit. So, here you see the data are basically traversing from this particular point. Okay. So, they are not dependent on each other, that means in this particular case they are interdependent, but in this case they are interdependent, that means P1 P2 is dependent on P1, P3 is dependent on P2, P4 is dependent on P3, but here P4, P3, P2, P1 all are individual case, they are not dependent to each other. Okay. So, this is the fundamentals of pipelining and parallel processing. So, again there are that means two type of that means pipelining technique. One is that coarse grain pipelining, another one is that fine grain pipelining. So, that means whatever we have seen in this particular case, that means this is one adder, this is one adder, right. In between of these two, that means at the connection level I am putting the resistor. So, in the operator level they are different, acting as two different adders at that time if I put the resistor in between path. So, this is basically known as coarse grain pipelining. At that time what is the limitation? That means I cannot reduce this more than the critical path that is restricted to the delay of this particular adder. So, that means I cannot achieve the clock period lesser than this. So, this is my that means the last critical path which or the maximum operating frequency of that circuit which I can achieve. But I need to increase the corresponding sample speed by more number. So, at the time what I will do? If I just break or if I just put resistor at the operator level, that means if I just break this addition operation into 2 or 3 or 4. So, at that time again I can reduce the corresponding pipeline, that means reduce the critical path. That means if I just consider over here, if I consider, that means at this time this is that means bounded to this adder delay. Now, if I put the resistor in between of this, so at the time this will be again become by 2. Okay. So, that means I can increase the operating speed of this by a factor of 2 if I use pipeline at the operator level. So, this particular pipelining technique is known as fine grain pipelining. Okay. So, if we take the example of that, so at the time you see this is one multiplier. Suppose this is the example of one this FIR filtering. So, here I need multiplier. So, multiplier if it is taking 10 nanosecond. So, at that time the delay, the critical path for this system, that is limited to the adder delay which is 2 and the 10 is the corresponding multiplier delay. So, the total critical path will be, if I do not use this corresponding delay in between of this multiplier. So, at the time it will be of 10 here and 2 here. So, total of 12 critical, that means nanosecond critical path. But if I just break this multiplier, so 6 over at the for M1 processing and 4 for the M2 processing, that means now I am putting this delay for this multiplier block. So, at that time the maximum of this is m 4 plus 2 6. So, over here is the 6. So, 4 plus 2 6 6. Now, the critical path will become 6. Then what will be the problem? That means, now here I am getting the speed up by again factor of 2. But the problem is that I am putting 3 extra resistor. At what cost basically I am getting? I am putting 3 extra resistor. Along with that, the latency is increased, that is again by a factor of 2. So, initially if these 2 were the, that means 2 was the latency, now it becomes not factor of 2, that means I have added one extra latency to the corresponding circuit if I use this fine grained pipelining. Okay. So, these are the, that means basic idea or the basic principle of this pipelining and parallel processing. So, this is one FIR filtering, that means parallel processing architecture of FIR filtering. Okay. So, for today this is it. Next day we will take one example. In the next class we will take one example and we will see how we can reduce the corresponding. We will start with one particular, that means the requirement of the critical path, then we will try to reduce how I can achieve the corresponding critical path by using pipelining and parallel processing. Thank you.